Hello everyone, this is the final project of our group. I am Liu Yugu, and we are gonna discuss about damped oscillation. First, let's make a brief introduction of damped oscillation. Damping refers to the loss of energy in an oscillating system due to dissipation, which can reduce or prevent oscillation. This influence can arise from internal or external factors such as fluid resistance, surface friction, resistance in electronic oscillators. Okay. In any oscillating system, damping causes the amplitude of oscillation to gradually decrease until the oscillation eventually stops. This process, where the mechanical energy is converted into internal energy over time, is known as damped oscillation. The damping ratio, denoted by zeta, is a dimensionless measure describing how oscillations in a system decay after a disturbance. It characterizes the frequency response of a second-order ordinary differential equation. In general, systems with higher damping ratios will demonstrate more of a damping effect. The damping ratio can be varied from overdamped, underdamped, critical damped, when the zeta is under 1 and equals to 1, respectively. When the system is overdamped, the amplitude decreases monotonically over time, and the system slowly returns to the equilibrium position without oscillating. On the other hand, the system returns to the equilibrium position as quickly as possible without oscillating, and we call this situation is critical damped. In this state, the system stabilizes rapidly. Furthermore, when the system is underdamped, that means the system exhibits damped oscillations, where the amplitude decreases over time, eventually returning to the equilibrium position. Okay, now we'll discuss spring damped oscillation. A block of mass m is attached to a spring with a spring constant k, with the equilibrium position set as 0, and then released from an endpoint, causing it to oscillate in a straight line on a horizontal surface, influenced by ground friction, damping force, and the spring's restoring force until the oscillation eventually stops.
Hello, this is Chen Ruichen. Now we're going to derive the formula. First, we introduce Newton's second law and calculate resultant force of friction and the force exerted by the spring. Then combine two equations. Let B, which is the damping coefficient divided by the mass of the object, is equal to 1 over tau, and omega, which is the natural frequency of an undamped simple harmonic oscillator, is equal to the square root of the ratio of the spring constant and the mass of the object. We can get this equation, which is the second-order linear homogeneous differential equation. Next, we derive the characteristic equation, and we can get N. Since it is critical damping situation, we can get zeta, which is equal to B over 2 multiply the square root of m multiply k. After we get n and zeta, it's time to derive the formula. When 1 minus 4 multiply omega to be the power of 2 and tau to be the power of 2 is smaller than 1, or zeta is smaller than 1, we'll get two complex roots. In this situation, it's underdamped. When the result is equal to 1, or zeta is equal to 1, we'll get repeated roots, and it's critical damped. Lastly, when the result is bigger than 1, or zeta is greater than 1, we'll get two real roots, and it's overdamped situation. We can get the formula x of t on the screen, respectively. Here's our results. First, we perform our results by MATLAB. First, we do some basic settings of our parameters, and then we define our motion equation. Next, we set our initial condition, and then do analysis of the motion equation. Finally, we generate the xt plot and vt plot, and here's our results. Next, we use VPython to do the simulation. First, we do some basic settings, and then set the parameters. Next, generate the graphs, and finally generate the animation, and here's our result. For the conclusion, based on the above-mentioned derivation of formulas and program verification, it can be concluded that the underdamped oscillation is not a periodic motion due to amplitude decay, while critical damping and overdamping do not produce oscillations. By observing the xt and vt graphs generated by MATLAB, it can be found that the overdamped case resistance is relatively stronger than the critical damped case, resulting in a slower speed at the same moment, and causing the overdamped oscillator to take a longer time to return to the equilibrium position. Here is our references. Thanks for your listening.